Hello and welcome to part 2 of the chapter 1 video lecture. We're starting with section 1.4. The previous video left off at 1.3. And I'll take a moment to remind you that the typed up video notes are available in Blackboard for you to print as opposed to you trying to write all of this stuff down. And it'll be important as you go through the quarter to have really good notes to refer back to, both for in-class work and for studying for quizzes and exams. So I would definitely strongly suggest that you print them out before proceeding with the video lectures. So we're going to look at objective A, which is to evaluate exponential expressions. Definition: the exponent indicates how many times the factor, which we talked about in the previous video, and the factor here is called the base, and we're looking at how many times it occurs in the multiplication. The multiplication, 2 times 2 times 2 times 2 times 2, and so there's 5 2's that are being multiplied together. That's in factored form when it's like that, which each factor is multiplied by each factor. But the expression 2 to the 5th, which is equivalent to this, is an exponential form because we have an exponent. So we're going to look at two different things, and students tend to struggle with the difference between these. So we'll put a little emphasis on it right now. Remember when we're talking about pemdas or gemdas, which is actually going to be objective B, but I'm sure you guys have learned it multiple times along the way through your education. There's a difference between doing something with parentheses and doing something without. According to pemdas or gemdas, you process what's inside first. Well, there's nothing to be added, subtracted, or anything together. But for purposes of what we're doing now, the 4, the exponent, is being applied to the entire base, and the entire base here is within parentheses. So here, the base is -2. Here, there are no parentheses, so the base is very different. The base is the thing that's immediately connected to the exponent. Notice that the 2 is connected to the 4, the negative is not. Over here, the negative is part of the base. So here, the base is just 2. And so you get two very different results, and that could affect the rest of your process if this was a longer problem. So we'll do this one first. So this is equivalent to saying -2 times -2 4 times, right? And so previously we learned that if you have an even number of negative signs, which we do, 1, 2, 3, 4, and 4 is even, then the answer is positive. So we're going to just ignore the negative signs at this point because we know the answer is positive. If you want to put a little reminder for yourself, you can put a little positive sign there. And now you go 2 times 2 is 4, times 2 is 8, times 2 is 16. And I'm only going to box the 16, and that matches our answer box there. Because we know that when there's no sign next to it, we have assumed that it's positive. Over here we have a very different thing, and I'm actually going to, I know you guys have already written it down, hopefully you write it in pencil. I'm going to actually move it. Base is 2. So I can put this little equal sign here. Now again we have something different, right? We have this negative, but then we have 2 times 2 times 2 times 2. And our answer is negative because there's only one negative sign. And 2 times 2 is 4, times 2 is 8, times 2 is 16. And we box the entire thing, and that matches our answer box. So this is going to come up multiple times throughout this quarter, whether or not you can tell the difference between taking something within parentheses to the exponent versus just taking part of what you think should be applied to the exponent. So make sure you definitely can understand the difference. Using parentheses is an important marker there. Objective V, to use the order of operations agreement to simplify expressions. Definition: an expression is a mathematical phrase that combines numbers and or variables using mathematical operators, which represents a value. It does not have an equal sign. So that's the biggest difference between an expression and we'll talk about later, which is an equation, is that an equation has an equal sign. An expression does not. Now you could add your little equal sign to the expression afterwards, but that doesn't make it an equation. So 7 plus 5 is an expression. There's no equal sign, and there are numbers, and there's a mathematical operator, which is the addition. And I will ask throughout this course, what's the mathematical process? What's the mathematical operator that's happening? And what I'm referring to is addition, subtraction, multiplication, or division. Those are mathematical operators. And even the fraction bar and parentheses and all those that help group things can be considered that. So we can also say, which we're going to look at later, 3x minus 5. That's also an expression because it has numbers and or variables. It has numbers and variables actually in this one. So those are just straightforward examples of what an expression can look like. So gemdas or pemdas, however you want to refer to it. Step 1 is perform operations inside the grouping symbols, and that's why I think some of the schools, some parts of the educational system have moved to calling it gemdas because we want to talk about grouping symbols. And grouping symbols extend well beyond parentheses. They include brackets, braces, which are these curly brackets, the absolute value symbols, and even the fraction bar is a grouping symbol because you're going to do the stuff on top and then the stuff on the bottom separate as if there were parentheses there. So that's why a fraction bar is a grouping symbol. You're going to simplify the exponential expressions, and this is the E part. So this is the G part, and this is the E part, and this is the MD, and this is the AS. So step 3 is multiplication and division as they occur. Now this is the key right here. So they occur from left to right for both multiplication and division and addition and subtraction. They occur from left to right. So don't start doing the numbers that are more convenient to do. When you're looking at multiplication, division, or addition and subtraction, you have to do them left to right. And so we're going to work on this problem a little bit. So we're evaluating this. And this doesn't have a lot of complicated stuff in it. It just looks complicated because it has several different grouping symbols. So you always start from the inner. Start from innermost grouping symbol. So the innermost is here. Now, I have a tendency to want to rewrite everything until I'm done. Students like to skip and then they get lost. So you have to find what really works for you. And I don't mean what works for you time-wise because you're in a hurry to get something done. I mean what's going to work for you on quizzes and exams and homework. More importantly, quizzes and exams, really. So I'm going to put a little equal sign here because all of this equals something, and we're going to start to simplify this. 18 minus 5, bracket, 8 minus 2. Now we're going to simplify, combine the terms within those parentheses, and hopefully you know that 2 minus 5 is negative 3. So it's very important at this stage to recognize what's happening. This is 18 minus 5 times 8 minus 2 times negative 3, and then the closing of the grouping symbols. This is not all of a sudden turn into 8 minus 2 minus negative 3. When there are parentheses between the negative signs, that means multiplication is happening. So multiplication won't always look like your typical multiplication symbol. Both of those equal multiplication. So now we continue. Now we do the innermost here. So negative 2 times a negative 3 is a positive 6. And then we're going to simplify this innermost grouping, which is 14. So now we have to take a pause. I took a pause because I realized this was going in a direction that I didn't want it to go in. And now I've realized why. I neglected an important piece of information for this problem, and we're just going to add it at the end. This is divide by 10. So this whole time we're dividing by 10 at the far right. So now we're at a point. So we're looking at, we've just been doing PEMDAS or GEMDAS, the G part this whole time, and some addition within the G. We've done the addition or subtraction or the multiplication within the G. But now there's nothing left to be done within grouping symbols. This is now representative of multiplication, and we have minus 5 times 14, but divided by 10. So we have to do multiplication and division from left to right. So some students are going to immediately say, oh, 18 minus 5 is 3, and then 3 times 14 is something, and then all that divided by 10. But remember that addition and subtraction comes after multiplication and division. So we can't quite combine these yet. But we can say that, well, negative 5 times 14 is a negative, and then we have to work on it over to the side. 70 divided by 10. And then continuing our very step-by-step process, we're looking at what's 70 divided by 10. Hopefully you know what 70 divided by 10 is. It's just 7. And now we're getting down to that answer that we were looking for this whole time, which matches our answer box, because 18 minus 7 is 11. So a few things that can mess you up along the way. Not having written down the entire problem, or not having written down the problem correctly could screw you up. And then incorrectly doing addition and subtraction before you've completed the multiplication and division will mess you up, or trying to do division before multiplication or something like that could mess you up. So just remember, go in order of the gemdas, and then multiplication and division is left to right, and addition and subtraction is left to right. And if you just follow that rule, you will get there. It may not feel like it, but you are getting there. Now we're going to take a look at section 1.5, factoring numbers and prime factorization. This section is really important, not just for Math 800 purposes, but for future purposes when we're talking about factoring rational expressions. So it's really important that you not rush through this section, that you really understand what's happening. So objective A is to factor numbers. Definition: a factor of a number is a natural number that divides the number with a remainder of 0. So let's take a look at the factors of 6. We're not looking for just prime factorization here. Right now we're looking for factors. So this is what I'm going to tell you to do. And this is how I process it, and I feel like I don't lose anything from processing it this way. I have seen students try to process it quickly another way, and then they lose factors along the way. I do bookends. So the first number you want to look at is 1, because 1 divides 6. And you create bookends. So you put 1 and its counterpart 6. And those are the bookends, and you're going to start working your way inward. So 1 times 6 is 6, and our next number is 2. 2 times what is 6? Well, 2 times 3 is 6. Now, once you've gotten so far in that there's no natural number left, and there's no natural number between 2 and 3, then you have found all your factors. And so what it means is that each of these numbers divides into 6 with a remainder of 0. Each of these numbers, 1, 2, 3, and 6, go into 6, divide 6 with a remainder of 0. So 6 divided by 1 is 6, remainder 0. 6 divided by 2 is 3, remainder 0. 6 divided by 3 is 2, remainder 0. And then, of course, 6 divided by 6 is just 1 with a remainder of 0. So now we're going to look at a longer problem. And I'm going to still do my bookends here. So we're going to say 1 and 24, and I don't know how long it's going to take, even though we have the answer box there. But I do know that 2 goes into 24, and how many times does it go in? 12. And if you don't know your multiplication tables off the top of your head, you're going to have to get that going. And then the next number, you just keep trying numbers if you're not sure. 3, well, does 3 go into 24? Sure, 3 times 8. And notice I'm working inwards. And now we're looking at 4, 4 times 6. Now the last natural number between 4 and 6 is a 5, and 5 does not divide 24. It gives you a remainder, and we can show you that. 5 goes into 24 4 times, and the remainder is 4. So that's not a factor because the remainder is not 0. So that creates our list of 1, 2, 3, 4, 6, 8, 12, 24. Before submitting any quizzes or exams or worksheets, you should be checking that all of these have pairs. There is a rare instance where the very middle term multiplied by itself will give you the number, but this is not one of those cases. So in this case, everyone should have a pair. So some students will know that 4 goes in, and then all of a sudden they'll leave out a 6 or they'll leave out the 8 because they're trying to think of all the numbers rather than pairing them up. So I think this method of working inwards will get you to every single factor, and you will not leave any factors out. Here's some maybe helpful factoring hints. 2 is a factor of all even numbers. So, you know, the even numbers 4, 6, 8, 22, 106, etc. If it's an even number, then 2 is a factor, okay? 3 is a factor of any number whose digits sum to a number divisible by 3. So we're going to try the number 102. That's a really big number, and right at the top of your head, you're going to start saying, well, I have to do this to actually see. But a quicker way would be to say, okay, 1 plus 0 is 1, 1 plus 2 is 3, 1 plus 0 plus 2 is 3. Is 3 divisible by 3? Yes. Therefore, 102 has to be divisible by 3. And we can actually follow through on this process here. And again, we're looking for a remainder of 0. So 3 times 34 gives you 102. Therefore, 3 is a factor of 102, and also 34 is a factor of 102. And you'd have to break the 34 down. But that might help you figure out some of the bigger numbers, some factors of some bigger numbers that we'll be working with, slightly bigger numbers. So 4 is a factor of a number if the last 2 digits of the number create a number divisible by 4. So if we try 104, where these last two numbers, 0 plus 4 is 4, and 4 is certainly divisible by 4. 4 divided by 4 is 1, remainder 0. Okay, so that tells me that 104 is divisible by 4, and in fact, no matter what numbers you put to the right, 3, 5, 8, 2, if these last 2 digits are divisible by 4, which is what this little quick and handy dandy rule tells us, then this whole thing is divisible by 4, and that can get you started on finding some factors. 5 is kind of quick and simpler. If it ends in a 5 or a 0, other than 0, other than just 0, then 5 is a factor of that number. So for example, 15, 5 goes into 15, 5 divides 15, but 5 also divides 20, and 20 ends in a 0, okay? And then we're going to move on to number 6. 6 is a factor of a number if both 2 and 3 are factors of the same number. And that's an important relationship to understand. If you have a number such as 36, 3 is a factor of 36, 2 is a factor of 36. Therefore, since both are factors, if you multiply them together, you get 6, and therefore 6 has to be a factor of 36, and we know that that's true. Let's see what else we can show. 24. We know that 2 goes into 24. We know that 3 divides 24. Therefore, 6 has to divide 24, and hopefully most of you understand that it does already. This rule right here isn't quite so helpful. I'm just going to read it off to you. 8 is a factor of a number if the last 3 digits this time of a number form a number divisible by 8. So that's asking a lot to know the last 3 digits, and you might just be better off dividing the number at that point to see if it's divisible by 8. 9 is a factor of a number if the sum of all the digits of the number is divisible by 9. So if you had a huge number, this also wouldn't be particularly helpful. But if we have this number, say 333, well, we know offhand that it's certainly divisible by 3 because 3 goes into each of these one time. So that's 111 times 3 would get us this. But it's not readily apparent that 9 divides 333. But if we take the sum, 3 plus 3 is 6 plus 3 is 9. The sum is divisible by 9. Therefore, this has to be divisible by 9. Now let's take a quick look. Let's see if we can prove it wrong. 3 divides 33 3 times because we need a 27. And that leaves us with a 63. 9 does divide 63. So 9 times 37 is this 333. And 37 is a prime number, so that's interesting that I chose that number. So this one again, 10 is a factor of a number if the last digit is 0 other than just 0. So no matter how big it appears, if the last digit is 0, 1, 2, 5, 8, 7, 9, 0, if this last digit is 0, then it's divisible by 10. And this is going to become very important when we're simplifying fractions. This becomes really important at that stage to know that quick and handy dandy fact. So objective B, we're going to move on to talking about prime factorization of a number. And let's just look at a definition. A natural number greater than 1, so you start off with 2, is a prime number if its only factors are 1 and the number itself. A natural number greater than 1 that is not a prime number is called a composite number. So you're either prime or composite, other than 1. The prime factorization of a number is the expression of the number as a product of its prime factors. product of its prime factors. So when we look at the number 2, 2 equals 1 times 2. So 2 is a prime number. Why? Because its only factors are 1 and itself. The number, you could say itself instead of the number. So we have 1 and itself. And so 2 is a prime number, and the same thing for 3 and 5 and 7, etc. So in fact, examples of prime numbers are 2, 3, 5, 7, not 8, because 8 is divisible by 2, not 9, because 9 is divisible by 3, not 10, because 10 is divisible by 2, so then we get to 11, and we get to 13, and it goes on and on. So composite numbers are the non-prime numbers. So what are we missing here? We're missing 4, we're missing a 6, we're missing an 8, and a 9, etc., etc. So it has to be prime or composite unless it's just 1, and 1 is not considered a prime number. So we all know the tree, I think. Most of us have learned the tree, the prime factorization tree along the way. But this textbook introduces a slightly different way of doing it, and I actually like the way it shows to do it. It's called a T diagram. And what you do is you break this down. And these are going to be your prime factors on this side. And on this side is the result of the division. So this is almost like a tree. Except that we're going straight down. So you're going to pick a prime factor that goes into 24, and the easiest thing always to start with is the number 2. And you're going to ask yourself, 24 divided by 2 is what? Well, that's 12. And you put the result here. And then you go, okay, now we're looking at 12. We did 24, and we're looking at 12. So 12 divided by 2, let's go again with the 2, is 6. And you keep going along the way. 6 divided by 2 is 3. Now 2 doesn't divide 3, so now we have to go to the next highest prime number, which is 3. Once you get to this point right here, you're done. 3 divided by 3 is 1. So this whole time, you're going across the columns. So 24 divided by 2 is 12. 12 divided by 2 is 6. 12 divided by 2 is 6. 6 divided by 2 is 3. 3 divided by 3 is 1. As soon as you get to a 1, you have your prime factors. It's 2 times 2 times 2 times 3, which is the left hand side. And this can also be written as 2 cubed times 3, which is what I have over here in the answer box. So it's your choice. If you want to keep using the prime factorization tree, that's fine. If you want to try using the T diagram, that's fine. However, I'll warn you, the prime factorization tree, if you get a relatively large number, students tend to lose factors. So if you're going to do the prime factorization tree, maybe I'll just do it up here. Here's the benefit by the prime factorization tree. You don't have to start with a prime number. You can start with any number. So I'll do 6 times 4. Neither of those are prime. So you keep going, right? That's how you learned. You keep going until you get to your prime numbers. One thing I'm going to suggest you do is as soon as you get to a prime number, you start circling it. Because sometimes you might get a prime number way up here, and then all of a sudden you've got all these branches. And you take the prime number as being at the bottom of these branches way down here, but you've forgotten prime numbers on the other side. So make sure you circle or write them down or highlight them or something so that you don't lose them. Otherwise, try the T diagram, because you definitely don't lose factors in the T diagram. So we're going to look at objective C, which is to find the least common multiple and greatest common factor. Students will tend to confuse these, so please practice, make flashcards, do whatever you got to do to remember the difference between the LCM or the GCF. So we're going to start with the least common multiple, LCM, of 2 or more numbers. Factors is the smallest number that is a multiple of all the numbers that we're looking at in the problem. The LCM is greater than or equal to the largest factor. So the LCM greater than or equal to largest factor, because we're looking at multiples. So in this case, our LCM has to be greater than or equal to our largest number, which is 36. So if you get into the habit of saying, okay, it has to be greater than or equal to the largest one, has to be greater than or equal to the largest one, and then do your process, you'll be less likely to confuse the GCF with the LCM. So we're going to start breaking down these numbers, and there's a couple of ways of doing this, maybe more than 2, really. So we can do this by prime numbers, and I'm just going to write these prime numbers down because I'm hoping that you guys know this. This is 9 times 2, and 9 is 3 times 3. So we can break this down like this. And 27 is 3 times 3 times 3. And 36 is 9 times 4, 4 is 2 times 2, and 9 is 3 times 3. So that's how I've done that. We have to find the multiple that has these numbers in it somewhere. So this can be written as 2 times 3 squared. This can be written as 3 cubed. And this can be written as 2 squared. That does not look like a square, but I want to make sure it looks like a square to you. 2 squared times 3 squared. We're going to take the highest degree of each of these to get to the LCM. So we're looking at LCM, take highest degree of the factors. So in our case, we have a 2 and we have a 3. We have to take the highest degree. The 2 occurs as 2 squared. That's the highest for the 2, for the base of 2. The 3 has 3 squared, and 3 cubed, and 3 cubed is the highest. So this equals 4 times 27, and 4 times 27 is 108. And you'll have to work out that 27 times 4. This is 28. You carry the 2. This is 8, 9, 10. And that's how we get the 108. Some of you are going to insist, because you don't like prime numbers and how to find prime factorization, of doing it this way. And then you go, okay, so this is times the 1, and then you have to do times 2, and then you're thinking, oh my god, 18 times 2, then I have to do this off to the side. Okay, that's 36. Oh, now I have to find 27 times 2. Oh god, that's 54. And I have to do, 36 times 2. Oh, I don't know what that is, so we have to do 12, and that's 6. Oh, now it's 72. Well, there's still nothing in common, and you keep doing this until you find the one that they have in common. So you're going to have to do this. You're going to have to do this one 2 more times to get to the 108. You're going to have to do this one a few more times to get to the 108. And this one, I think you just have to do 1 more time to get to the 108, because 36 times 3 is 108. So there's something here, there's something here, there's something here, and then all of a sudden here there's 108. And then that's when you circled that, right? But there's a lot of scratch work involved. Now, yes, when you're doing your homework or any other work that's outside of the classroom, you will probably try to use that calculator of yours. That will not do you any good for when you're on a quiz or an exam, because calculators will not be allowed. So the sooner you get adjusted to picking a method that's going to work for you long term and practicing that method, the better off you will be. So the end result is that the LCM is in fact 108, and match our little answer box here. Now we're going to compare that to the GCF. The greatest common factor, GCF, of 2 or more numbers is the greatest number that divides evenly, and I mean with a remainder of 0, into all the numbers. The GCF can be found by first writing each number as a product of prime factors, and then the GCF contains the prime factors common to all numbers. And the one thing I left out here is that the GCF should be less than or equal to the smallest number. So let's take a pause and go back up to our prior problem. Remember up here we said, oh, the LCM has to be greater than or equal to 36. Was it? Yes. The LCM was greater than or equal to 36. In fact, it was greater than 36. So now we have to find something that's less than or equal to what? Our smallest number. And our smallest number in this case is 18. So our GCF cannot be bigger than 18. So again, we're writing these as prime factors, which I've done previously. So this is 2 times 3 times 3, or 2 times 3 squared. And this was 3 times 3 times 3, or 3 cubed. And this was 2 times 2 times 3 times 3, or 2 squared times 3 squared. This time we're taking the ones in common. That's why it's called common factor, the greatest common factor. And sometimes it's easier to do it this way than this way this time. We're going to circle the ones that they have in common. They have this 3 in common because each one has 1. They have this 3 in common because each one has 1. This one and this one have a 2, but this one doesn't have a 2, so it's not in common. Even though there's an extra 2 down here, we can't just move it willy-nilly. So our GCF is our circled things multiplied by each other, which is 9. Over here, you want to take the lowest exponent of the common factor. Lowest exponent of the common factor. Factors. So what are the common factors here? 2 is not a common factor, again, because 27 doesn't have a 2. 3 is certainly a common factor. We're taking the lowest exponent. We have a 2, we have a 2, and we have a 3. Which one is the smallest number of those? Well, just a 2. And that also gives us a 9. Both of those match our answer box. It doesn't matter which way you choose to do it. You just have to remember not to confuse the LCM and the GCF. The LCM took the highest exponent. The GCF takes the lowest exponent. And let's do our reality check. We said at the beginning that our GCF had to be less than or equal to 18. And in fact, we got our GCF was equal to 9. Is that less than or equal to 18? Yes, it is. So our reality check checked. And here's 1.6. But instead of proceeding with 1.6 in this video, since we're at about 31 minutes right now, I'm going to terminate this video. And this will be part 2 of the chapter 1 video lecture. And then we'll proceed with part 3, which will start with this section 1.6. So we'll see you in the next video.